Hello, everyone. Welcome to Module 6, Session 2 of the ML Foundations course. Our speaker today is Jo-fai, so if you have any comments or questions for him, please make sure to use the chat or the Q&A box. So with that said, I will hand it over to our speaker. Joe?
Hey, thank you, Franklin. Hi, everyone. So again, thanks for joining us again today on this Module 6. So this is the module about responsible AI with H2O-3 and Java's AI. So my colleague Ben talked about how we use Java's AI so in the last sessions. So this session here, I want to show you how we can use the open source H2O-3 to do some of the explanation for our models. So personally, I'm quite excited to show you this because these features in H2O-3 are quite new, like a few weeks old. So today, what you see today are some new features in our latest release, and I'll give you a quick introduction of the features, and then I'll spend most of the time on explaining how to use it with some examples. Now, I'll do a quick recap, and I'll tell you what's next in this foundation course. So let's go over a quick overview of what you can expect from this session. So you're here. So you are in the module 6. So frankly, you have gone through a long journey in the AI and ML foundations. So we're trying to give you some hands-on examples on how to frame your business problem for machine learning, how to wrangle your data. We have some basic on machine learning and deep learning, and I'll talk about how to use Spark with H2O, sparkling water last time. And this one is about how to explain some of the models that you produce using H2O-3. And hopefully this will be useful for you to trying to explain your model to other people in the future. That will be again over the weekend a study group and Ask Me Anything sessions with Sam. And please make use of those if you have more problems or more questions about content. As usual, there will be quizzes after the sessions. So I'll show you some of the highlights of the examples, and the quizzes is all based on the same tutorial or same some example. So you don't need to run anything, but I hope that you can actually try to install H2O and try to run it with your own data set. So we're trying to answer just one key questions here is that why should I trust your model or why should you trust my model? So many people nowadays see that machine learning models are just like a black box system, meaning that you have some inputs, meaning you have inputs like your features of the models. Could be like for a credit card example, could be the age of the applicant, or could be the application of the applicant, some inputs, and then we fit them into a black box, and they come out with some predictions like whether we approve your credit card applications or not. But this is not helping with others to make decisions because they see this as a black box. So what we want to do is to use different tools to try to make this more transparent. Try to take this black box away into a more like a glass box, and this is the goal of this module. We try to make people trust the model that we built from the data. Let me just use two very simple example here. The first one is on the top. It's about explaining just one individual predictions to other human beings. So for example, you have a model predicting whether patients had flu or not. So we have some feature in either does he or she sneeze, the weight, and then does he or she had headache, etc. And then we use that to build a model, and then we predict that okay, this patient has flu. But sometimes this is not enough. Sometimes we want to take this model to the next level, which will include the explanations of the model, saying, okay, because we have seen this patient with sneeze and headache, some symptoms like that, and then we can kind of quantify those impact, quantify the contributions of different features into the final outcome, and then we can use that to pass it on to the next decision maker. So it could be a nurse, could be a doctor. Here, and then they can try to kind of understand what we're trying to do with the machine learning model. So that's for like individual predictions. And the other way is to look at it is that sometimes you need to look at whole model as a whole. For example, how do this model make decisions based on different scenarios? So if patients have different symptoms, what will the model predict in the future? So there are two different ways to look at this. So that we can call this either local explanation and a global explanation. So these are the two terms that I want you to remember for these sessions. Just a bit more on the terms that we are using in these sessions here. So, responsible AI is a really big area. So we are not trying to cover every single things with the tools that we are discussing today. And there are also like a subtle difference between explainable AI and interpretable machine learning, because people may use them like at the same time or in different kind of situations. But for me, today we want to focus on explainable AI, which we try to quantify some of the weights, some of the decision-making weightings from the models. So that is the main goal for today's sessions. And if you want to dig deeper into more kind of explain the inner workings of the model, that is more towards the interpretable machine learning. So although they're most often used together, but I want to make clear that today is about the quantifications of some decision-making weightings. Okay, so that's a quick overview. And now let me just introduce these new features, these new toolkits in H2O-3. So some of you may have read about our blog post. So this is the major release blog post. We did it just 2 weeks ago. So all the features are quite new. So even though I haven't tried everything yet. So for example, there's a new algorithm called Roofit, and then we also have other cool things in this new release. But today I want to focus on one of the main inclusions in this release, which is the model explainability toolkit that we have. So I want to thank my colleague Erin and Thomas. So they are the masterminds behind all the tools and all the tutorials that you will see in the next few minutes. And if you want to read about the blog post, this is the link to the blog post. Okay, so what do we have here? So basically, we try to do the two things that I mentioned about. So the local explanation and the global explanations with two very easy to use API or interface. So what we try to do is to provide a simple wrapper to give you some explanations globally and locally with some like really nice graphs. What we try to do here is just to help our users to explain the model quite easily with just a few commands. And you also have the same functionality in both Python and R. So today I'm going to show you the Python versions, but you can also find the example notebooks in R Markdown from the same repository that I'll show you later. And of course, if you want to read more about all the functionality in this toolkit, just go to our website, to the documentation website, and you will find a lot more explanations about this. So let's start with the global explanations. So we try to make it easy, super like simple for people to fit in the models. So you can see that for the API in out and Python, all you have to do is to fit in either a single model and then the data sets that you want to explain. And that's it. So that could be like a lot easier than other toolkits that you may have seen from other vendors. But we try to make it into one single API call to explain a single model with multiple graphs. Sometimes you want to compare actually multiple models from H2O. So it could be like the whole set of models from AutoML. So you can also do that. You can just fit in the AutoML object into this explain function, and it will try to compare different models for you with the explanations. So these are how we do it with both R and Python. And so mainly we want to highlight that we can explain either a single model and multiple models using the same API. And this is for the global explanations. Then, of course, after the global explanation, you want to do like a single prediction, explain a single predictions. And in this case, we have a different functions, but it's almost the same. So this time you have to explain underscore road. So we want to point it into just a single road. This time, one single sample this time, and try to explain how the model come up with the final predictions based on different inputs. So that's how we do it with R and Python. So you put it again, you can point to either a group model or just a single model, look at the test data set, and then look at the actual row that you're interested in that test data set. So that's how you can pinpoint to one single predictions and try to explain it. So that's now we have global and local explanations. So of course, there are a lot more so there are more parameters that you can do to trick the way that you want to see the plots. And you can also create individual plots. If you don't want to see the whole thing, then you can also do that with the R and Python API. So I'll leave this to you for you to explore of all the parameters and all the functions that you can do with this new functionality in H2O-3. So that was a really quick introduction to the model explainability toolkit in H2O-3. So I want to focus now on some examples. So I believe that this is the most useful part for beginners to try to make use of our toolkit by learning from the examples. So let's start with a simple data set. So some of you may have seen this before. This is the wine quality data set. It's not really big data set, very typical for learning machine learning. You can look at this is like a few rows from the data set. You see that there are different kind of characteristics of the wine. So for example, the sugar level, the acidity, the density, the pH, and the alcohol, and then either is a red wine or white wine. So these are the features that we want to use to train this model. So it's a supervised learning problem. So we have a target as a quality. So I think it's from 0 to 10. So it means really, really bad. And then 10 is the top quality wine. So we want to create approximation of the functions from these features to the target here. So we use H2O to build models for that. So if you want to find out more about this dataset, just go to this link here. And we also have the CSV file on our S3 folder. So you can just use that. So after these sessions, I will need you to go back to this notebook again. So the things that you see in the next few minutes are all based on the same notebook. But I just highlight some of the key API calls and key graphs that you need to pay attention to. But then when you need to finish the quiz, you need to go to the main tutorial on our GitHub repository and just go through the notebook in your own time. Okay, so let's start with the model building. So this is not the most important part because you probably have seen this before. We're trying to build AutoML model, lots of models using AutoML using the wine quality data set. So we import the files from S3, and then we say that this is the target we want to look at. This is the quality column, and the rest of them just the features. So to predict the features, we're using all these features from dataset to predict the quality. So then you could do the usual. You can split it into a training set and test set, and then you can just set off AutoML to run it for 600 seconds, and after that you have a list of model like that. So you have probably seen it before. So just create a list of model, and then we also have 2 stat ensemble at the end of the process. So what we want to do next is to use the new functionality in H2O-3 to explain the models here. So it could be any of the model, could be the stat ensemble, could be the XGBoost, or could be the list of model together, like a comparison. So let's start with the first easy example, just trying to do the global explanations on one single model. Okay, so this is how we can do it in using Python. So first of all, if you don't have the model object already, you can use the h2o.get_model to extract or to get one of the model from the list. It could be any model, could be XGBoost, could be a random forest. So I just picked the XGBoost here for the example, but you can try to do this with other models from your own data set. And then you can just use the first command here, just explain this model with the test data. So if you do that, that will give you all the ports here. It will just generate all the relevant ports for explanation for you. But sometimes you may not need all the ports. You may want just some of the individual ports. So you can also do that with the model doc, and then you just use different functionality here to port individual graphs here. It's up to you. But I'll probably use that most of the time because it's quite easy. And now let's go through individual ports, and let me explain how you can use it to explain your model. The first one is, so probably you have seen it from other toolkits, is a residue analysis of the regression problems. So what we will see here is a graph showing so some fitted value here, so from 3 to 8. So these are the predictions. These are the numbers coming out from the model. So you can see they're real numbers. So this is a distribution of the numbers from the model on the test set. And on the left-hand side here, on this axis here, you see the residue of the predictions when compared to the actual target. So what we are saying here is that, for example, for the numbers that the model predict about 5, you mostly see that some of them they're really 5, or they could be 1 plus 1 or minus 1. So they could be 6 or 4 in the real targets. So what we see here is, so 5 is like a more probably easier target in this data set. So you may be 1 off, but then you're not too far off when compared to maybe like here. So for example, this could be 6.4, 6.5 something. But then when you have a prediction about 6.4, then you may have some really large error. So you could be like 3 or maybe minus 2.5 off the actual target. So this is just a simple analysis to look at the errors from the predictions when compared to the actual target. And what are we looking for here? We want to look at the residue if they are randomly distributed. The reason why that we want to do that, so this is like another toy example here. So if they are randomly distributed, that means that there's no like obvious trend from the lower value of the predictions to the higher value, or the other way around. So there's no trend between the actual value of the predictions and the residue. So we want to do that because we want to make sure that these errors are random. You will see that they may not look too random here because the actual target here is integers. That's why you can see that it's always like a gap between 1 here. But if you have another problems that they have the real values as the target, then you'll probably see something like this, more randomly distributed. And then most important line you want to see is that blue line here, which is like report a trend here across all the point, and then we still want to see that that's close to 0, like just a horizontal line here, and that's what we want to see from a good model. If when you analyze your model, you see something like a trend, like could be this simple linear trend or other shape. If you see an obvious trend, then that means that your model is kind of biased towards different factors. So that in that case, you want to think about how to reduce that kind of that trend in the residue, and try to make them into try to create different models and make sure that they have a random distributed errors or residues when you plot this graph. That's the first graph. And this is something that you may have already seen from a previous version of H2O-3. It's just the variable importance or the global importance of different features. So this is kind of handy because you can take this to any of the expert, or like in this case, the wine expert, and you can ask them whether they think that alcohol is one of the major factor to determine the wine quality, whereas the density and the pH value, they are less important in terms of the wine quality. This is something that when you build a model, when you don't have the domain knowledge of the business problem, you can use this graph to communicate with other domain experts. So that's the second graph. So now this one is more like really, really important, because this is called the sharp summary, and sharp is like this is the actual name of the sharp value here. So it's sharply additive explanations. So this is based on the optimal sharply values from game theory. And this is very robust. You can see more info from this book here. But more importantly, if you look at where the origin of the Sharply net value is from the late Lord Sharply. So he went these Sharply values here, and he won the Nobel Prize for that. So this is very robust on how we can look at different contributions of different features to the predictions. But you may ask, how do we read this graph? So let me just go to the next slide, and then let me explain how you can read it. So for example, if you look at the top feature here, the alcohol feature here, and we look at the color of the feature. So the color, when it's more pink, that means it's like a higher value of the feature. So in alcohol, to be the highest feature of high value of alcohol will be around in this area, whereas the lower value of alcohol are mostly in this area. So that means when alcohol is high, so when you have a high value of alcohol, they have positive contributions to the prediction. So they are more likely to contribute to higher wine quantity, because this is the end target. So higher is with the value is higher, it means better wine quality. On the other hand, if you look at the lower value, so when you have the blue color here and light blue color here, those dot here, so they are more likely to contribute negatively to the final value. So that means that you can expect that if you have a lower alcohol value in the wine, then you may also expect lower wine quality. So that's one way to look at this sharp summary. And each dot here represents one single example of the in the test data. And then you can also look at the other feature as well. So for example, you look at the next feature on the list here, the volatile acidity, that is like the other way around. So if you have a lower volatility of exit, then you expect actually a higher quality. So there's like different ways to look at different features and how they contribute to the final predictions. Okay, so that's the third graph. Let's move on to the next one. So this is like another important graph that you may want to use to explain your models. This is called a partial dependence plot. So similarly, if you think about the example we look at about alcohol from the sharp summary, this is also kind of explaining the same story, but from different techniques. So what we're trying to do here in this graph is look at one feature at a time, and the actual response, meaning the predictions value from that alcohol, from this feature. And so look at the mean response of predictions when they have different alcohol value. So you can see that when the alcohol value is low from here, generally you can expect a lower response here, which means the lower wine quality value. When it goes up, when the alcohol value goes up, you expect a higher wine quality. So this actually kind of reinforced the message before. Like we saw that from the previous graph here, we saw that when you have a higher alcohol value, it means it could mean higher wine quality. And then on the other way, when you have a lower alcohol value, you have a lower wine quality. So the next part here actually give you about the same story. So this is good because you have two kind of different plots, or you can look at the same thing from two different angles to tell you the same kind of findings from this model. So you can tell people now that your models, this model here, the XGBoost here, is doing this thing here. So when you have higher alcohol value, it will just give you higher wine quality in general. So of course, you can also look at the other features. So I'll let you explore that for the quiz question. So, but you see that some of them you can see an obvious trend, and some of them they may not be too obvious. After a few waves. So this could be useful part to give you some evidence of the model doing something that you expect from the domain expert. So let me move on to the next one. This is actually quite similar to the partial dependence plot, but this is called the ICE plot, the individual conditional expectation plot. So very similarly, if you look at the dotted line here, this is just like the same graph that you saw before. This is like the partial dependence plot, which is using the mean response of the predictions based on the algorithm. But the main difference here is that we put different percentiles on the same graph. So this will give you a bit more information. So more juice for you to decide whether there's interaction between this feature and the final predictions. Because if you just look at the mean response, sometimes you see a rather smooth curve. You don't see the whole picture. But for example, here you will see that when you put into different percentile, that you may see kind of like a step change from different values here. So that could be like some new area, some new evidence that you may want to validate with the domain expert. You want to see that, we want to make sure that this kind of behavior is expected also from the domain expert. So this, again, giving you more information to explain the same kind of story from different angles. Okay, so we talk about the different graphs for the global explanation. So the next example here is the opposites. So this one we want to focus on one single example or single explanation. So what we want to try to do is look at predictions like here. So we use H2O model. It could be other models in the case, but this time we don't want to explain the whole model. We just want to point it into the test data set, and this first row in Python 0, this is 0 base, but the first row of that test data set, I want to have some explanation of how different features contribute to the final predictions. And then we have two graphs. So again, the chart here, this is a bit different to the chart summary that you see from the global explanation, because this is now based on just one single predictions. But what you can see is that the actual contributions, you can quantify the impact or different weight of the model have from different values of the features. So these are the actual value of the features in that example. So based on that, you can just sum up all the values here, plus the bias term, which is like a constant value. So if you sum up everything here, you will get to the prediction here, which is about 5.9, about 6. So this is how we get to the explanation. Say, okay, now we have the first row of the test set the model is giving a prediction of 5.99. How do we explain that 5.99? So you can see that about 0.14 something is coming from the free sulfur dioxide, etc. And then, different kind of features, they have different contributions. And now we can actually put a number, we can quantify that for the other decision maker. So we can have that, this is some of the most important features. So we have the most important contributions. There could be a positive contribution on the side, or it can also be a negative contributions on the other side. So that gives you a picture of how the model is using different features to come up with the final predictions, which is 5.99. So this is very, very useful when you need to look at individual predictions. If you think about other than the wine quality, if you think about like the credit card example again, this could be one applicant. Let's say this is Joe. This is Joe going to a new bank, trying to apply for a credit card, and then so if I don't get the card, the bank can use some tools like this to explain to me what are the factors that that they use to make the final decisions of declining my credit card approval, and they can show you different features that have different kind of contributions, and that's why we give you a final predictions of not good enough to get the credit card. So something like that, I think this is something useful that you can reuse it for your own research problem. You can also use it to explain single role to different people, and hopefully this will help them understand your model, and they will trust your model a bit more, and then they can use it for actual real life decisions. So that's the sharp for local explanation. The next graph here is similar to the IC plot, but we only focus on a single instant here, so single prediction here. So we see that this is about the alcohol, and the alcohol value is about 10.1 here. So we look at alcohol 10.1, and then we know that this is about 6. So we know that the general trend is about when you have a higher alcohol value, you got higher wine quality, and then this kind of giving you another view of the same story, saying that, okay, if you have alcohol value around 10, then you probably expect something like this, 6. Okay, so that's the local explanation. So I show you the tools. So for a single model, you can explain globally and locally. So this is kind of giving you some numbers to explain your models. Okay, so the final example here. So this is more like a comparison of different models. So we try to compare different models together and look at how different models have different kind of contributions to the final predictions. But before that, let me look at the Q&A here first. I can see 2 questions here. Okay, the first one is about the histogram, the background. Okay, let me go back to that. So we know. Let me go back to that. Yeah. Yeah, so I think this is something that we need to improve in the next version of H2O, as that we don't have enough explanation about the histogram here. So if you imagine that this histogram is just the actual distribution of alcohol, of the value alcohol from the test set. So in test sets, they mostly have value from 8 point something to 13 point something. Yeah, so that's the distribution of the alcohol value in the test set. So hope that makes sense. So I guess we need to have a bit more information here to help our users understand what is going on with the histogram. But this is just the distribution of the feature that we are looking at, all the values that from the test sets we're looking at on the same graph. So hopefully you understand this by now. Let's see if there's any other questions. Okay, so let's move on to example 3. Okay, this time we don't want to look at multiple models together, and this is how we do it. So in this case, we're just using all the models from the first AutoML object. So we have the whole object here, put it into explain, and then we want to use a test set for the explanation. So this is how we fit the whole thing into the explanation toolkit. So first of all, you will see just a little board here. Again, you can show you a different kind of model ID here, and then the performance on the cross validations. And so you also see the time for training, and then also the time for prediction as well. And if you want to look at individual map or individual plots, you can also use this function here in both R and Python to do individual plots. But I always use this here just to simplify the process to plot everything in one go. So let's look at some comparisons. So this is the first one that will show up. So it's called the variable importance heat map. What we're trying to do here is to look at taking all the models together and see what are the most important features in individual models. And all you see from the heat map is that so the red here is the most important, and then the blue here is less important, right? So you see that most of the model here, they don't really care about the type. So type is really low importance for most of the models. And then if you look at alcohol, then you see that it's really important for some of the models. So it's really red here. See for the GBM here, for the William Boosting machines models, they're very important. But then they are less important in some of the other models. So for example, in XGBoost, it's still important, but not as important as the GBM. So that you will see that using different algorithm, they may extract the information from different features differently. And that's a good thing to keep it more diverse. So this is like a quick overview of how different features and the importance for different models. So this is also quite useful when you try to say if you want to create a group of models that are more diverse with different kind of importance in features, then this is like a good check, a good first check to see, okay, maybe I don't want to have too many GBM together because they are like really similar in terms of using a lot of depends on a lot on alcohol. Whereas if you mix a bit of different thing together, that may give you kind of a higher diversity. So the next graph here is this time is trying to compare the correlation between different models. So for example, you got a lot of models here in the AutoML object. Then you see that the diagonal is always 1 because you're trying to compare the same model together. So that's why this is also always dark red with 1 coefficient equals to 1. But then now you can look at how the same model here, the GBM, is correlated to different models. So for example, when I compare GBM to XGBoost, so it's less correlated. So that's a good thing. So we don't want to have too many models correlated together to build a final example. And that's like another quick look for you to make sure that they're not highly correlated in the same ensemble. So for me, I can see that there's the first key finding I will find or say from this graph is that the state example here is really correlated to the extreme random forest here, the XRT here. So that could be one of the reasons could be the XRT could be the highest performance model from the bunch. So the rating for the XRT could be really high. So that means that the XGBoost, the XRT model is very similar to the final ensemble. So although this is still better in terms of the performance, but it's too correlated to just one single model. So if I have to rebuild this, if I have to redo the exercise again, I may try to make it one longer and try to and hopefully it will try enough different combination of the algorithms to make it more diverse. So this is how I would use the correlation model graph. Okay. So after that, you have one more plot. So this is like comparing different models using the partial dependence plot. So again, now let me look at the questions again. So you still cannot grab the histogram. So if think about the histogram as the actual value, the density of the alcohol value from test set. So that could be like 10,000 samples in a test set, and each of them they have a different alcohol value, right? So this histogram is just like the density of the alcohol value from the test set. So unfortunately, we don't have the axis here to show you the actual density value. But then that means that if you look at this graph here, I can tell you that there are a lot more examples in the test set with alcohol value about 9.6 something. So this is like still a lot more a lot of value of alcohol value of 9, and there are less value of alcohol value of 13 in this data set. And that's how I can read this histogram. So there are more alcohol value around this area than those high alcohol value. So I hope that makes sense to you. Okay. So back to this graph here. So what we're trying to look at here is how the models are different in terms of the partial dependence plot. So we look at the alcohol value. We expect that the lower alcohol value will have a lower mean response rates, the wine quality, and then vice versa. We have a higher value here when the alcohol values go up. But you can see a very subtle difference between different algorithms. For example, you can see that the tree-based model, so the extreme random forest, the random forest here, and then the GBM, XGBoost, they're all tree-based, as well as the stack ensemble, because they're quite similar to the extreme random forest anyway. So they kind of have the same kind of shape here, so it's non-linear, and get like kind of like a step change in here that become like a group of different models that goes up in a very similar way. And if you look at the other models, like the generalized linear model, you can expect just a linear line here, just a line for GLM. And then for the deep learning model, they're actually quite close to the GLM. It's also quite linear when they go up. So it's quite different when you look at the deep learning model, the behavior of the deep learning model, the behavior of the GLM, and the behavior of the other groups of like the tree-based model. So that's what we can read from this graph. So different kind of behavior on alcohol from different kind of algorithms. So let me look at the questions again. Okay, this is done. So it just the distribution is just based on the actual number of values. So it's just histogram of the alcohol values. So that's we don't have. I don't know how to explain it more. So so this is like we're trying to understand single models, but you can fit the stat ensemble as well. So let me just go back to the plot here. So let me go back to the example here. So here you can actually fit the stack ensemble here because all you need to do is look at the name of them from the side. Let me just go through here. So all you need is to get the name from the leaderboard. So it could be any of the models here. It could be the stack ensemble. It could be the GBM. So all you need to do is to get the ID of the model and fit it into the code that I got here. Just get the model, and you can explain the model, including the stack ensemble. There's a question about the correlation here. So yeah, again, red is the high correlation. So 1 is like the same. So when you compare the GPM group 1 model 61 to itself or the same model, then you get a dark red, which is 1 because you have the perfect correlation to yourself. And then when you compare the model with other models, then you get something different. So it's from 1 I would say between 1 to 0.8 in this graph here. Because most of them, if you look at the list here, they are mostly tree-based model. So we expect that they're quite similar on this graph here. Okay, so let me look at the question again. So done this. Okay, so I think I answered most of the questions now. So let's get back to the. Okay, so finally, let me just do a quick recap of these sessions. So we go through some of the major questions. So why do we need this? Because we want people to trust our model. So no matter what you say about how good your modeling tools is, some people still think that we are just doing black box model. No, it's fine because in some way it's a black box. When we have a set ensemble, deep neural network, they are really complex thing to just explain it in a few sentences. But that's not the end of the world because we do have other methodologies to explain the model. That's why we introduced this model explainability toolkit in H2O-3. So it's open source, everyone can use it. The main features here is that we can do a global explanation, whether it's a single model or a bunch of models from AutoML. You can also explain just a single role here, again, for single model or multiple models. So this will help us kind of make it more transparent, saying how can we relate the input to the final predictions, and how can we show these numbers, quantify them, and try to discuss them with the decision makers or other domain experts. So we have a toolkit here for you to use it. And again, all the example here are based on the same tutorial notebook on our GitHub repository. So you will get the slide here, and I'll also upload the instructions for the quizzes. So you get the link again and all the instructions that you need to finish the quiz questions. But this is the main repository that you need to go to, either the R versions or the Python versions. So that's most of it. So let me tell you what's next. So again, we have the quiz, and then we have study group and ask me anything over the weekend. And the next module is about ML ops. So how you use our tools from H2O to deploy and to manage and govern different models in a production environment. So this is also a important step in this AI journey, because once you train the model, you need to make sure that you have a systematical way to deploy it, to make use of it. Otherwise, we just stay on your computer for a long time, without making being used by other people. So we want to have a way to deploy them, make sure that they're actually useful for making real life decisions. And here are some additional resources. So again, we have our documentations and then the blog posts about this new release. Check this out, because there are other cool features as well that you may want to try out. And then you got, again, this is the tutorial that I want you to look at for the quizzes. And this is a nice book that about different kind of technology or different kind of framework that you can use to interpret your machine learning models. And of course, we also have our open resources. Our colleague spend a lot of time on this kind of resources. So we have a book and 2 white paper. So do check them out, because they are like how you can actually link the things that you learn from this AI course to real life use cases. So these are quite valuable resources that you can learn more about how we can apply the skills here on the real life business problems. So, okay, so let me look at the questions again. So the first question is about, so what exactly adds Java's AI to explainability? The post I see here seems rather complete. I think we are missing a lot of functionalities in H2O-3 still. The long-term goal is to make them converge, so we will have more and more functionalities in H2O-3. But then I think in Java's AI, the ease of use. So when you click on the graph about the explanation, there are more explanations from just a few clicks from Java's AI, and I think that is more useful for business users, for doing this at scale. When you have a bigger team, not all of the team members can use H2O-3 for all this stuff. But I understand that there is a kind of overlap between open source and the commercial product Java's AI. But that's not a bad thing, because we're trying to learn from the market as well. So we try to implement different features in the products and get a feedback. And then we know that from the actual feedback, some of the graphs here that we can do. And for example, if I go back to here, so some of the graphs here will be really, really helpful for people who know how to do programming in R and Python. So we want to include that with H2O-3, but we cannot include everything that we have from Java's AI in the same framework. So but at least we're trying to do our best to make them converge in the long term. So you may expect that there will be more and more features from Java's AI slowly moving to H2O-3. So we're trying to give back to the community as well. But at the same time, we're trying to evolve quicker on the commercial product, so we get more feedback from our customers first. So that's not like a easy business problem, but I think actually over here we enjoy the success from both sides, from like growing the H2O-3 communities and also growing the customer base for Java's AI. So there's a question about which correlation part. You said high correlation between model is not good. Yep. Okay, let me go back to that. So this is the graph here. So like imagine if you have a graph here full of like red scalar. So for example, they all have about more than 0.8 or 0.85 correlation with each other. That means that your final ensemble is not kind of diverse enough in terms of choice of the models here. So if I have a choice, if I have to have more time to do it, maybe I will try to force the AutoML process to include different algorithms. So maybe a bit more models from the deep learning side, maybe a more linear model as well. So make the selection here more diverse for the set ensemble. That usually, in my experience, that usually helps. It's not always the case, but if I have a set ensemble that's highly correlated, at this time it's highly correlated to just one single model. This is like the extreme random forest here. Then I may not be too confident about how this will achieve the best performance in real life. But that again, that could not be may not be the case for all the data sets. So again, if you have more time for the AutoML, give it more time to try different algorithms, and hopefully you'll see a more diverse graph here. So maybe a bit more light color, maybe a bit more blues here. So the second example, you can see that it's built on a more diverse set of base models. Yeah. So again, I hope you guys enjoy sessions. I want you to try this H2O-3 new features, the model explainability toolkit. It's quite new to me as well because I only spent the last few days trying to figure out how it works, and it's fantastic. I think it's a really great addition to your toolkit if you're already using H2O-3 models. And of course, you also want to relate this to your real business problem. So I guess this kind of this resource, this book and white paper here are also a very fun learning resource for this topic here. So if there's no other questions, I think we can wrap up here.